Now I want to revisit a concept that we talked about in T-line analysis, and that's the idea of skin depth, which is the depth to which the electric field can penetrate material. And we noticed that this is what was primarily due to, or this is the primary factor that causes wires to have what we call an AC resistance, which is often considerably higher than its DC resistance. And we know that our AC resistance is a function of frequency. And what I had told you was that, if we've got a conductor, the E field can only penetrate a certain distance into the conductor, meaning that current's only flowing in this outer perimeter of the conductor, meaning the whole cross-section of the conductor is not available for conduction of electricity, and therefore the effective resistance is high. Why does this happen is the question that I'm posing here. So let's consider the geometry of a conductor. And we've got along the length of the conductor, orient the conductor along the length here, and we've got a conductor here, Z. We've got, coming out of the conductor, we've got Y, and then we've got the x-axis going in that direction. And so we've oriented our conductor in this orientation, and basically what we want to say is that, what's the value of the field here at the front end of the conductor if we're just looking at it in 2 dimensions. And we're going to label those. We're going to say that we've got, call it EX0, and then the magnetic field's in the Y direction, so we'll call it the EY0. These are just the initial values of the fields. i.e., it's the value of the fields at Z equals 0 if going across this thing is the how deep we can go into it, right? So we know from the phasor form of the plane wave solution that we've got E bar x is equal to E bar plus, in the x direction, e to the minus gamma z. So that's that forward wave component. And so we're just going to plug this in here. We get E bar x is equal to whatever the initial value of this electric wave was right there. It's then going to, since this is real material, we can plug in alpha plus j beta. Right, and this wave's traveling, in this case, it's trying to get to the center of the conductor. So this is this forward traveling wave here. And we'll just separate these parts. E bar x is equal to EX0, the initial value again, e to the minus alpha z, e to the minus j beta z, right? So this is the wave trying to make its way in. So for a conductor, you'll remember in the last slide we saw that alpha equals beta for a conductor, and that's equal to omega mu sigma over 2. And remember, omega is just 2 pi f, so that's equal to pi times f times magnetic permeability times sigma. And plug that into that equation right there. You'll get Ex bar is equal to, whatever the initial value is, e to the minus pi f mu sigma z e to the minus j root pi f mu sigma z. Right. So that's the wave. Well, what's the amplitude of the electric field strength at any point? That's just this portion right here. So I would say that the amplitude of that wave is just equal to, well, whatever the amplitude of the initial value is. And then we need to multiply that by just this decaying exponent. And So here we could just do a little bit of rewriting. And I'm going to just let delta equal -1 over root pi f mu sigma right there. And what this is showing us is that the skin depth, delta, comes from the magnitude of the electric field as it penetrates into the conductor. And since it's an exponent e to the, what this delta shows us is that this is the depth that the E field will fall to 1 over E of its value at the surface, which is about, it's going to decrease to about 37%, of its initial value. And so what this is saying is if we plug in numbers here, we're going to get a depth, and if we were to go that far into the conductor, the E field has fallen off to about 37% of whatever the value was at its surface. And it's due to this effect right here, the skin depth. And we can make some observations about skin depth. Skin depth is going to decrease as permeability increases. Skin depth decreases as conductivity increases, which is an interesting analysis. Better conductors have smaller skin depths, and skin depth also decreases with frequency. And so the higher the frequency, the less the current can get into there. So we focused on this before. Higher frequencies caused the electric current to not be able, the E field to not get into the conductor very well. Turns out highly permeable materials have the same problem, but most interestingly, highly conductive materials have the same problem. So this property here, since F is in the denominator, this is why conductors have an AC resistance and a DC resistance. And resistance of a conductor is going to therefore increase with frequency because the net area over which the current can flow is reduced. So as an example, let's determine the skin depth of water at 1 megahertz and 20 kilohertz. So the skin depth of water, delta at 1 megahertz, is equal to 1 over pi times 1 e to the 6. Water has a relative permeability of 1. And then the conductivity of water, it varies depending on the impurities in the water, but let's just go with a ballpark estimate of 4, and we get a skin depth of 0.2516 meters. So I inject a 1 megahertz signal into water, it drops off 37% of its initial value after 0.2516 meters, so not particularly far. If I were to put this in terms of attenuation, what's the attenuation at, let's say, 10 meters? I would say I've got 1 Nieper, 0.2516 meters times 10 meters times 8.686 dB per meter. So I've just taken 1 Nieper, I've divided it by the skin depth, I've then multiplied it by the distance over which we're measuring attenuation, and I just chose 10 meters. And then I've just done a dB to meter conversion. I find that at 10 meters at 1 megahertz, I've got 345.23 dB of attenuation due to salt or due to water. What about at 20 kilohertz? Well, the skin depth at 20 kilohertz is going to be 1 over, everything's going to be the same except this frequency, pi times 20 e to the third. And you do that and you get a much deeper skin depth, 1.179. These are in meters. And then the attenuation at 10 meters is just going to be 1 over 1.179 times 10 times 8.686. And that's going to give me attenuation of only 48.83 dB at 10 meters of my initial E field strength. So considerably less than at a higher frequency, which I think serves to illustrate the effective skin depth.